Hello everyone, my name is Riccardo Michielan and I am a postdoc at the Gran Sasso Science Institute in L'Aquila, Italy. And today I talk about the planted clique problem on geometric graphs. So let us start from a little bit of motivation. The idea is that malicious actors operating within network systems are posing a growing threat in an increasingly hyper-connected world. And the main challenge then is to identify these malicious nodes before they cause irreversible damage to the network, using scalable and efficient methods, and at the same time committing very few mistakes. Now, the point is that sometimes it's easy to spot malicious agents and sometimes it's not. For instance, when we are working within a network system with low graph density, but we have a large anomaly, this is easy to spot because it naturally emerges and everyone can see it. On the other hand, when the graph density is much higher and the anomaly size is much smaller, it is also much more subtle to spot. So we define formally the problem mathematically by introducing three parameters: n, which stands for the number of nodes in the system; k, which stands for the size of the planted anomaly, in our case it's a clique; and mu, which is the density of the graph, that is, the average number of connections in the graph. The proxy is the following. We first generate the graph, spreading n nodes uniformly at random, and connecting them if they are sufficiently close to each other. This is called also a random geometric graph with density mu. Secondly, we plan the clique. So we select k vertices at random and we force them to be all pairwise connected, forming what you can see here on the right in this picture. So now the question reads as, under what assumptions on n, k, and mu can we detect the planted clique? The results we got were after investigating two different algorithms. The first idea was to use vertex decrease. So if the planted anomaly requires to have additional connections, this means that anomalous vertices also have larger degree. So you simply find the k vertices with the largest degree in your network and you assume they form the anomaly. The second idea is to use common neighbors. That is, if you look at the common neighbors of two anomalous vertices, these common neighbors should also be anomalous vertices. And both of these algorithms are very simple, but more importantly are very efficient because the first one is linear in the size of the graph. The second one is quadratic in the size of the graph. And our results show that vertex degree algorithm performs quite well almost always when k is large, but performs badly when the density of the graph increases, so when mu is large. On the other hand, common neighbors approach works almost every time, which is very interesting. So the conclusion we could also observe by a numerical experiment is that in all cases, so for mu small, average, or large, which are respectively called sparse regime, connectivity regimes, or dense regime, the common neighbor algorithm outperforms vertex degree algorithm, but most importantly, it performs very well all the time. So this is an immediate application meaning. That is that in geometric graph, there exist simple and efficient algorithms that can quickly spot malicious agents in network system. So thank you for listening to my poster presentation, and I hope to see you in Rome at the final conference of FAIR.